Alright, so now we're going to deal with improper integrals. And the first kind of improper integral I'm going to deal with is an improper integral where the limits of integration are infinite. So, here are the three cases. The three cases are, the first case is where the upper limit of integration is infinity. If the upper limit of integration is infinity, then, well, that is a problem because when we defined our integration, our definite integral, we said that there had to be a closed interval from a to b for us to do the integration, and the interval from a to infinity is not a closed interval. So therefore, we come up with this definition for the definition when we want to take a limit, or when we want to do an integral where the upper limit is infinity. So we have this definition for a limit where the upper integral is infinity. We have this definition for an integral where the upper limit of integration is infinity. This is definition 1. So when we have an integral where the upper limit of integration is infinity, we're actually going to calculate that integral using this limit. The second case is where the lower limit of integration is negative infinity. If the lower limit of integration is negative infinity, we're going to use this definition. And the third case is where the limits of integration are negative infinity to positive infinity. And in that case, we're going to use this definition where we split the integral up into two parts with some real number c on the interval from negative infinity to infinity. So let's take a look at an example. The example I want to look at is the integral from 1 to infinity of 4 over the 4th root of x dx. So the first thing you notice is this is an improper integral because the upper limit of integration is infinity. So since the upper limit of integration is infinity, I'm going to rewrite the integral using this definition. So this is actually equal to the limit as b approaches infinity of the integral from 1 to b of 4 over the 4th root of x dx. So that is what I'm actually going to do. So let's go ahead and calculate the integral. So this is the limit as b approaches infinity of, let's rewrite this as the integral from 1 to b of 4 times x to the negative 1/4 dx. That makes it a little bit easier to calculate the integral. Now we can use just the power rule. So upon taking this antiderivative, I get that it's equal to the limit as b approaches infinity of, and then this antiderivative is actually going to be 16 over 3 times x to the 3/4 power, and I'm taking this integration from 1 to b. Taking that integration from 1 to b. So this is going to be equal to the limit as b approaches infinity, of, well, let me see, when I plug in b, I get 16 over 3 times b to the 3/4 power, and then minus 16 over 3 times 1 to the 3/4 power, which is equal to the limit as b approaches infinity of, let's see, this is going to be 16 over 3 times the 4th root of b cubed minus, and that's just 16 over 3. So now I have to do the limit. Well, when I do the limit, I'm going to do direct substitution. I get that this is 16 over 3 times the 4th root of infinity cubed minus 16 over 3, and any root of infinity is equal to infinity. So this integral is equal to infinity, which means that the integral actually diverges. This integral actually diverges. So this integral diverges because it's equal to infinity. So that is the application of the first definition. Let's take a look at another example. We see that that integral diverges, and the integral diverges because its value is equal to infinity. Let's take a look at another example. Okay, the second example is the integral from negative infinity to 0 of e to the 3x dx. E to the 3x dx. Well, by the definition, well, this doesn't fit the first part of the definition. This fits the second part of the definition, where I'm going from negative infinity to some real number b. So I'm going to rewrite it using that part of the definition. It's going to be the limit as a approaches negative infinity, the limit as a approaches negative infinity of the integral from a to 0 of e to the 3x dx. Alright, so that is the integral that I am looking to do with the limit in front. So let's go ahead and do the actual integral. Well, this is a u substitution. We have here the limit as a approaches negative infinity. And when you do your u substitution, u is going to be 3x, so du is going to be 3 dx. You need a 3 in here, which means you're going to put a 1/3 in the front. You're going to put a 1/3 in the front. And the integral of e to the u, du is just e to the u. So when you integrate e to the 3x dx, you get 1/3 e to the 3x, and this is going from a to 0. From a to 0. So now I'm going to plug in my limits. This is going to equal the limit as a approaches negative infinity of 1/3 times e to the 3 times 0 power minus 1/3 times e to the 3 times a power. 3 times 0 is 0, and e to the 0 is 1, so this is equal to the limit as a approaches negative infinity of, this is just 1/3 minus 1/3 e to the 3a, and now I'm going to take the limit as a approaches negative infinity. Well, as a approaches negative infinity, this is what we're going to get. Direct substitution yields this: 1/3 minus 1/3 times e to the 3 times negative infinity power. Well, when you raise e to the negative infinity power, that's like 1 over e to the infinity, and 1 over the e to the infinity is 0. So this entire term right here, this entire term just goes to 0, leaving the answer 1/3. So this limit here is equal to 1/3. So this limit converges, or this integral, sorry. This integral converges, and it converges to the number 1/3. So that's how we're going to handle integrals with infinite limits of integration.